Ever wonder how your brain spots a face in a crowd, or how AI figures out what makes a cat a cat? It's all about finding patterns in the noise. Today, we're diving into a study that reveals how restricted Boltzmann machines, a type of neural network, learn to lock onto stable patterns, even when the world around them is constantly changing. Let's break it down. So RBMs are like the brain's detective squad. They have two layers, one that processes raw data like a photo of a cat, and another that learns abstract features like whiskers or ears. But here's the twist, they don't just memorize data, they adapt. Think of them as puzzle solvers that adjust their strategy when the pieces shift. Now imagine training an RBM to recognize cats. The network has to ignore distractions, like different lighting or backgrounds, and focus on the consistent features that define a cat. This is where place cell emergence comes in. Just like neurons in your hippocampus fire when you're in a specific location, RBMs develop specialized detectors that lock onto these stable patterns. Even if the data changes, these detectors stay sharp, like a detective who always knows where to look. Here's the cool part. The study shows RBMs don't just stumble upon these patterns. They systematically refine their detectors through a process called dynamic adaptation. It's like training a dog to fetch a ball. Each attempt gets them closer to the perfect throw. The network adjusts its internal weights, the strength of connections between units, to sharpen its focus, even as the data evolves. To test this, researchers used a model where data constantly shifts, like a game of musical chairs where the rules change mid-game. They found that RBMs don't get confused. Instead, they recalibrate, developing detectors that stay tuned to the invariant features of the data. It's like a musician who adapts to a new melody without missing a beat. Why does this matter? RBMs are the unsung heroes of unsupervised learning, where machines learn without explicit instructions. This research shows they're not just passive learners, they're active problem solvers, constantly adjusting to stay ahead of the noise. It's a glimpse into how AI might one day mimic the brain's ability to adapt and recognize patterns in real time. So next time you see an AI recognizing something complex, remember, it's not just learning. It's adapting, refining, and evolving, just like we do. Thanks for watching. If you want to see how this plays out in real data, check out the experiments in the paper. Until next time, keep exploring. Let's dive deeper. Imagine training a machine to learn from data. At first, it's like a blank canvas, everything is possible. But how does it figure out what's important? This is where statistical mechanics comes in. Yep, that's the same physics that explains how gases behave or why ice melts. Here, it's used to study how RBMs adjust their internal connections, like a map of all possible strengths between neurons. Think of the weight space as a vast, hilly terrain. Every point on this landscape represents a different way the network could be configured. At the start, the RBM is in a symmetric state, like a perfect snowflake, where all connections are equally likely. But as it learns, something magical happens, the symmetry breaks. Some connections grow stronger, others fade, creating a structured pattern, like the snowflake melting into an asymmetrical shape. But here's the twist, this isn't a one-way street. The research shows RBMs can dynamically restore symmetry when faced with new data. It's like your brain adapting to new experiences while keeping old knowledge. Imagine learning to ride a bike. Your muscles remember the balance, even when you're on a different path. This balance between stability and flexibility is key to how RBMs stay effective over time. Now, let's talk about the big discovery. The study identifies a critical threshold, a tipping point where the RBM suddenly shifts from failing to learn to mastering patterns. This is tied to something called the BBP transition, a concept from random matrix theory. Think of it as the moment the RBM wakes up, unlocking hidden patterns that were previously invisible. It's like turning on a light in a dark room, everything becomes clear. To visualize this, picture our snowflake again. At first, it's perfectly symmetrical. But as it melts, it becomes chaotic. Yet when new snow falls, it reshapes itself, restoring balance while adapting to the new environment. This mirrors how RBMs adjust their weights, balancing old learning with new data. So why does this matter? Understanding these processes helps us build smarter, more adaptable AI. Whether it's improving medical diagnostics or enhancing recommendation systems, the math behind RBMs is quietly shaping the future. Thanks for watching, stay curious, and keep exploring the science that powers the world around you. Let's unpack the mechanics. Think of neural networks as a team of detectives solving a mystery. Each hidden unit is like a detective scanning a crime scene. At first, they might all focus on the same clue, overlapping too much, like a group of detectives all staring at the same fingerprint. But here's the clever part. During training, there's a mathematical manager at work, tweaking how these detectives interact. This manager is called a regularization term, mathematically written as WQW. It's like a boss who encourages diversity of thought. If two detectives are too similar, say, both fixating on the same clue, the manager nudges them apart. But if they're conflicting, like one thinks the suspect is tall and another thinks they're short, the manager might actually pull them closer. This back and forth ensures the team isn't stuck in repetitive patterns, keeping their approaches fresh and adaptable. But here's the catch, the detectives also need a compass. That's the eta1H term, which acts like a GPS pointing them toward the actual signal, the real clue they're supposed to find. It's a balancing act, too much disalignment and the team loses focus. Too much alignment, and they risk missing new angles. What's fascinating is how this plays out over time. Early in training, the detectives might clash, but gradually, they fine-tune their interactions. Equation 139 shows how each detective adjusts their strategy based on their overlap with others, a feedback loop refining their roles. By the end, the team isn't just memorizing clues. They're dynamically adapting, uncovering patterns hidden in the noise. Next time you see a neural network tackle a complex task, remember, it's not just about data. It's about this invisible dance of alignment and disalignment, guided by math, turning chaos into clarity. Science right.